The story of our becoming human began slowly in Africa around 7 to 9 million years ago. At that time, the being we now know as human had not yet emerged. It would also take millions more years before the first humans took their initial steps toward domesticating animals. Research by paleoclimatologists has shown that between 7 to 9 million years ago, the face of the African continent was dramatically different from its present-day conditions. At that time, a large portion of what we now know as the Sahara Desert was covered in dense forests. These forests were home to a wide variety of animals, especially diverse groups of primates, commonly referred to as monkeys. In addition to primates, there were other species of animals living in Africa that have since become extinct. With the cooling of the polar regions of the Earth and the subsequent decrease in seasonal rainfall in tropical areas, the forest cover in Africa began to change. Gradually, this led to the destruction of dense forests, and over time, grasslands and woodlands expanded. These climatic changes resulted in the creation of an environment that we now call the savanna, a vast land with tropical and subtropical climates, covered with grasslands and scattered trees or shrubs. Environmental changes in any region lead to two significant occurrences in nature: extinction or the emergence of new species. Living organisms in each area, in response to changes in their environment, either fail to adapt to the new conditions and continue their existence, leading to extinction, or, by chance, undergo a positive genetic mutation that enables them to adapt. In this case, the bodies of some members of the group undergo small changes that allow them to survive and reproduce, passing these beneficial traits on to future generations. This is how living organisms diversify over time, giving rise to various forms of life. Genetic mutations in the genes of living organisms continuously occur throughout their lives and reproduction due to various reasons. The effects of each mutation can be categorized into three scenarios. Either the mutations have no impact on survival, are beneficial for survival, or are harmful. If a mutation is harmful, it leads to the death of the organism, such as a bird being born with a deformed wing, unable to fly. In this case, the bird is very likely to be hunted by other animals before reaching maturity and finding a mate, preventing it from passing on its genes to the next generation. In other cases, mutations may have no significant impact on survival, such as the different eye colors in humans, which result from various genetic mutations. Regardless of eye color, all humans have the ability to survive in nature. In the third scenario, genetic mutations can benefit the survival of an organism, helping it to adapt to new conditions, reproduce, and pass its genes to future generations. One of the most notable examples of this type of mutation occurred during the Industrial Revolution in Europe for a species of moths in Britain. Before the Industrial Revolution, due to the lack of pollution, most of these moths had light-colored wings, which allowed them to blend in with rocks and tree trunks, effectively camouflaging themselves from predatory birds. This trait aided their survival and enabled them to reproduce. However, with the onset of the Industrial Revolution and the increase in air pollution caused by fossil fuels, the situation changed. The pollution darkened and covered the surfaces of rocks and tree trunks with soot, making it harder for light-colored moths to camouflage themselves. As a result, they became more exposed to predatory birds, and their population declined. On the other hand, genetic mutations consistently produced moths with dark wings, which had previously been disadvantageous for survival and reproduction, leading to the elimination of those carrying this mutation. But after the environmental changes, this trait, dark wings, helped moths blend in better with the soot-covered environment, allowing them to survive longer. Consequently, these moths reproduced more successfully. Over time, dark-winged moths became dominant, and their population increased. This shift illustrates how a genetic mutation can benefit the survival of a species under new environmental conditions. Throughout the history of life on Earth, most living organisms have gone extinct due to their inability to adapt to new environmental conditions. The faster these environmental changes occur, the less time organisms have to adjust to the new circumstances. According to scientists' estimates, more than 95% of all living species on Earth have become extinct. Biologists refer to the process of the diversification of animals and plants over time as evolution. This process explains how species, in response to environmental changes, undergo genetic modifications over time, leading to the emergence of new species. Until the mid-19th century, some scientists throughout different eras had only made scattered and mostly incorrect guesses about how evolution occurs in nature. Eventually, this hidden mystery of nature was uncovered by Charles Darwin, one of the greatest and most famous scientists in human history, and Alfred Russel Wallace, independently and simultaneously, in 1859. Darwin and Wallace, in their quest to understand how organisms change over time, the process of evolution, argued that through sexual reproduction, organisms give birth to offspring that are not exact copies of their parents and have differences from their ancestors. These differences, known as biological variation, allow organisms to respond to the demands of their surrounding environment. When the differences between offspring and parents exceed a certain threshold, the emergence of a new species occurs, a process known as speciation. In nature, there has never been enough space and resources for all species, leading to a struggle for survival. Therefore, only those species that possess the highest level of adaptability, or at least the minimum necessary adaptability to survive in the new environmental conditions, are able to continue living. This principle is known as the survival of the fittest, or natural selection, which forms the foundation of Darwin and Wallace's theory of evolution. With the changing environmental conditions in Africa, early primates underwent genetic mutations and speciation, leading to diverse groups. Many primate species eventually went extinct, but some underwent changes and evolved into new species, continuing their existence. Around 6 to 7 million years ago, a group of primates appeared in Africa that could walk on two legs, had smaller canine teeth, and larger brains compared to other primates. These primates and their descendants were called hominins. In contrast, another group that lacked the anatomical adaptations for bipedalism eventually evolved into modern chimpanzees and bonobos. It is no coincidence that humans and chimpanzees share the highest genetic similarity among all living organisms, 98.6%, as the common ancestors of humans and chimpanzees diverged only about 7 million years ago. In other words, modern humans, scientifically named Homo sapiens sapiens, and chimpanzees share a common ancestor. Paleontologists rely on 3 types of evidence to reconstruct the past of human ancestors. First, fossil evidence, which consists of the petrified remains of ancient living organisms. Second, geological evidence, which includes characteristics of the environmental conditions where our extinct ancestors lived. By analyzing geological layers, scientists can reconstruct past environmental conditions, such as climate, vegetation, and even natural events like volcanic eruptions or floods. Lastly, cultural artifacts, including stone tools and any signs of activities performed by hominins during their lifetime, such as fire remains, provide insight into how our ancestors interacted with their environment and what tools they created and used for survival and daily life. To explain how a fossil forms when an organism dies, what remains of it is usually scattered by environmental factors like wind, water, and scavengers. Over time, the soft tissues and bones are decomposed and destroyed by bacteria, fungi, and other microscopic organisms. However, sometimes the carcass of a dead animal may be covered by sediments, such as river silt, lake, or swamp mud, which helps prevent the immediate destruction of the remains. In this case, while soft tissues like muscles and other organs do not last long and decompose, under certain conditions, the hard parts of the body, such as bones and teeth, can become fossilized and preserved. During the fossilization process, the organic materials in the bones are gradually replaced by minerals from the sediments, turning the bones into stone, which can remain in that form for a very long time. Due to this protection over time, fossils of ancient organisms are found only in sedimentary geological layers. Fossils discovered in a given area, if not transported there by other factors like water currents and belonging to that location, can provide significant insights into the past life of that region. When these three types of evidence are considered together, they provide a comprehensive picture of the life, evolution, and environment of human ancestors, helping anthropologists to reconstruct human history with greater accuracy. Archaeologists use various methods to determine the age of fossils. Generally, dating methods can be divided into two categories: relative and absolute. In relative dating, by knowing the age of a geological layer or having an object with a known date, and ensuring that the fossil in question did not come from another layer, for example, through flooding. Scientists can estimate the fossil's age relative to the geological layer. This method only allows for an approximate estimate of the time period during which the organism lived. In absolute dating, archaeologists use complex mathematical formulas and knowledge of the half-lives of radioactive elements to determine the exact age of a sample. One of the most common methods in archaeology for absolute dating is the use of carbon-14 dating. Archaeologists can determine the calendar age of an organism's death with minimal error by sending samples containing organic material, such as bones, skin, hair, and teeth, to dating laboratories. A notable limitation of carbon-14 dating is that it can only date specimens up to about 45,000 years old. Additionally, it requires the presence of carbon-based organic material, making it unsuitable for dating mineral fossils that lack organic components, such as rocks or carbon-free fossils. For fossils that lack organic material, archaeologists use other methods: argon-argon and potassium-argon dating. These methods are particularly used for dating volcanic rocks and minerals. 1. Potassium-argon. This method is suitable for volcanic rocks and minerals and can date samples up to approximately 1 million years old. 2. argon-argon, an advanced version of the potassium-argon method, offering greater precision and capable of dating samples from several million years ago. Other techniques include luminescence dating, which determines the last time mineral grains were exposed to sunlight. Anthropologists have discovered a variety of hominin fossils dating back approximately 7 million years and beyond, with some living at different times and others concurrently on Earth. For a long time, scientists believed that human evolution and the evolution of our ancestors followed a linear and progressive path. They would place each new fossil sample in chronological order based on its geological age, creating a sequential arrangement of fossils, with each fossil considered as an ancestor or descendant of the others, to map out a linear evolutionary trajectory for humans and their ancestors. It is now clear that not all hominins represented by the fossils we have were on a direct path to becoming modern humans. Some hominin species lived alongside those that eventually led to modern humans for hundreds of thousands of years before going extinct. In reality, the evolutionary path of human ancestry is not a linear and straightforward process, but rather a complex, branching tree with numerous branches diverging from the main trunk. The story of human evolution is a complex and fascinating one, filled with various hominin species that once lived on Earth. These species interacted with one another and, depending on their environment and abilities, either went extinct or evolved in different ways. Ultimately, around 30,000 years ago, modern humans emerged as the sole surviving member of this ancestral lineage. Archaeologists have named the periods when hominins used stone tools the Paleolithic Era. This era began around 3.5 million years ago with the earliest pebble tools used by a hominin species called Australopithecus afarensis, and ended about 12,000 years ago with the advent of animal husbandry and agriculture. The Paleolithic Era is further subdivided into 4 distinct periods based on changes in subsistence strategies, stone tool forms, and hominin diversity. 1. Lower Paleolithic, approximately 3.5 million to 400,000 years ago. 2nd. Middle Paleolithic, approximately 400,000 to 40,000 years ago. 3. Upper Paleolithic, approximately 40,000 to 18,000 years ago. Fourth, Epipaleolithic or Mesolithic, approximately 18,000 to 12,000 years ago. This classification primarily applies to ancient sites in Africa, Europe, and Asia. The presence of humans in other parts of the world, such as Australia and the Americas, occurred much later and is associated with different cultural and technological developments that are not included in these divisions. The Paleolithic Era is a key period in the history of human evolution, marked by significant advancements in technology, culture, and subsistence. Studying this era helps us gain a deeper understanding of how humans lived, had progressed, and changed, as well as recognize the impact these changes had on the course of human evolution. During the early Paleolithic period, archaeologists have identified 6 species of hominins, each playing a specific role in the evolution of humans. These species include Australopithecus, Homo habilis, Homo rudolfensis, Homo ergaster, Homo erectus, and Homo heidelbergensis. This diversity among hominins highlights the complexity and ongoing changes in the path of human evolution. In the upcoming videos, we will delve into the lives of these extinct hominins that once roamed the earth. During the Paleolithic era, the use of stone tools marked a pivotal moment in the evolution of hominins. The creation of stone tools not only helped hominins acquire high-quality food sources such as meat and bone marrow, but also enabled them to adapt more effectively to their surrounding environments. These tools allowed hominins to modify their surroundings and manage food resources more efficiently. In the early Paleolithic period, around 3.5 million years ago, life on Earth had expanded to a new type of hominins within the heart of Africa. At that time, various hominins were simultaneously exploring and experiencing the world. Each of these hominins, with their unique characteristics, tells a fascinating story of evolution and adaptation. The Paleolithic Era, the longest period during which hominins lived on Earth, serves as a reminder of a story of progress and survival. During this time, which spanned millions of years, hominins developed various tools to adapt to different environments. One of the most remarkable features of this era was the widespread use of diverse materials for tool making. Although hominins also created tools from wood and bone, these materials have largely decomposed over time, leaving fewer traces. In contrast, stone tools have endured, surviving millions of years, which is why archaeologists have named this period the Paleolithic, or Stone Age. So far, 2 distinct tool-making industries from the lower Paleolithic era have been discovered and identified by archaeologists. The first is the Oldowan industry, which is older and simpler, and the second is the Acheulean industry. In the 1960s, archaeologists in a valley called Oldowan Gorge in Tanzania uncovered the first simple stone tools, such as chipped pebbles and stone flakes, leading to the identification of the lower Paleolithic period. This discovery marked the beginning of the recognition of the Oldowan tool-making industry. Since then, whenever tools with similar structural characteristics were found and dated to the lower Paleolithic era, they were attributed to the Oldowan industry. The tools from the lower Paleolithic era tell the story of the earliest attempts by hominins to enhance their skills. These tools included thin flakes with sharp edges, which were detached from larger pieces of stone and used for shaping wood or bone and for cutting meat from bones. Additionally, there were also cobbles used for breaking skulls and long bones of animals. According to the latest research published in 2014, the first hominins to create and use these types of tools were a species of Australopithecus known as Australopithecus afarensis. Other hominins of the lower Paleolithic era, including Homo habilis, Homo rudolfensis, Homo ergaster, and Homo erectus, also used the Oldowan industry for making stone tools for hundreds of thousands of years. Interestingly, studies of chimpanzee and other ape behaviors have shown that they sometimes use tree branches as simple wooden tools to extract termites from holes or use rocks to crack open nuts. It has also been observed that sharp-edged flakes are occasionally detached from larger stones during strikes, although these flakes are rarely used by chimpanzees. The key difference between these behaviors and the use of Oldowan stone tools is that making stone tools requires skills beyond the simple abilities of chimpanzees' brains and hands. Crafting Oldowan tools involves striking with the right amount of force, at the correct angle, and in the precise location on the stone. This process reflects a level of planning and precision in tool-making that significantly surpasses the natural skills of chimpanzees. The next tool-making industry that emerged during the lower Paleolithic was the Acheulean industry. This industry represents a significant and innovative advancement in stone tool technology and dates back to approximately 1.7 million years ago. Named after the Saint-Acheulean site in northern France, where these tools were first discovered, the oldest evidence of this industry, however, has been found in Africa. In the Acheulean industry, tools were made by striking oval-shaped cobbles with multiple symmetrical blows. These precise and controlled strikes on both sides of the stone resulted in the cobble taking on an almond or tear-shaped form. These tools, which were made in various sizes and used for nearly 1.5 million years, are known as Acheulean hand axes. Hominins such as Homo ergaster, Homo erectus, and Homo heidelbergensis used these hand axes for a variety of tasks, ranging from butchering animal meat, breaking animal bones, digging soil, and perforating materials, to working with wood and even potentially attracting attention from others. Scientists, through detailed studies of some of the most beautiful and largest of these hand axes, have discovered that many of these tools were never used. It is possible that their creators made these exquisite hand axes simply to showcase their skill in tool making. It is not an exaggeration to bestow upon these toolmakers the title of the first ancient sculptors. To create such tools, the maker had to visualize the shape of the hand axe in their mind before beginning the work on the pebble. With great skill, much like a sculptor creating a statue from a large shapeless stone, they meticulously removed smaller flakes from the pebble to shape it into a bifacial teardrop form. An important point is that achieving the skill to create such remarkable tools was possible only through continuous learning and observation of numerous examples, as well as through the process of tool-making itself. These skills were passed down to subsequent generations and required learning through observation, practice, and the transfer of experiences. The makers of these tools reached this level of skill and precision by viewing and imitating previous examples, and through ongoing training and practice. Scientists also believe that tool-making had a significant impact on the complex development of the brain in our human ancestors. Theories suggest that the simultaneous evolution of tool-making technologies, language, hand control, and the brain played a crucial role in this process. Alongside advancements in tool-making techniques, another significant development in the Old Stone Age that profoundly affected all aspects of the lives of those early human ancestors was the control of fire. Archaeologists have discovered the earliest evidence of fire use from around 1.5 million years ago in southern Africa. This suggests that Homo habilis likely had the ability to control and maintain fires, which could have been sparked by natural events such as lightning. They probably used fire for cooking meat and plants, making them easier to chew and digest. However, there is evidence indicating that Homo heidelbergensis had mastered the continuous use of fire around 800,000 years ago. This implies that by that time, human ancestors had acquired the knowledge to ignite fire themselves. When early hominins in the Old Stone Age began to consume cooked food regularly, this behavior reduced the evolutionary advantage of having large jaws and teeth. With the removal of natural selection pressures on jaws and teeth, these features gradually became smaller over time. This change occurred because there was no longer a need for large teeth to effectively chew raw meat and tough plants for survival, growth, and reproduction. Fire took over this role, making it easier to process food. Additionally, cooking food made digestion and nutrient absorption easier, reducing the workload on the digestive system. As a result, there was less need for a long, large intestine. The energy saved from the reduction in gut size was redirected to the brain, which continued to grow and become more complex, leading to cognitive and cultural advancements. Another significant benefit that fire provided to early hominins was the ability to sleep more deeply and for longer periods at night. Fire served as an effective deterrent against predatory animals, keeping them away from hominin groups. This allowed them to sleep more soundly and deeply, with less fear of nocturnal dangers. Deep sleep has played a crucial role in enhancing memory and cognitive functions in humans. Interestingly, the fascination with kindling fire and gathering around it has persisted through thousands of years and remains a cherished activity for us humans. This behavior, with its deep-rooted origins, continues to be embedded in our culture and habits. It serves as a profound link to our past and endures in contemporary life. The increasing complexity of the brain, thinking ability, imagination, and language have been crucial for the survival of human ancestors in nature. Early human species had to create everything necessary for their survival. In the wild, they were defenseless creatures. They lacked the sharp claws and teeth of carnivores, the speed of deer and gazelles, the flight capability of eagles and hawks, and the burrowing ability of small rodents. They could no longer quickly take refuge in trees like their primate ancestors and slept on the ground at night. The only strength of human ancestors was their increasingly complex brains. The complexity of the human brain and its positive outcomes in facing a changing and dangerous environment, which continually threatened the survival of early defenseless humans, was the most significant factor in the survival of our species and our ancestors. The lower Paleolithic era is a fascinating period that holds many secrets about how we became human. Archaeologists strive to uncover pieces of this incredible story by delving into this era. Through meticulous excavation and examination of every small detail from this time, they seek answers to fundamental questions. Who are we? Where did we come from? How and why did we reach this point in history? These efforts help us gain a better understanding of ourselves and our place in this complex world.